Shall I?
Yasmin ma'am, it takes just a few seconds to actually start streaming live.
Okay.
So I'm just taking that time.
Oh, okay. It is doing that, is it?
Yeah. So it will
Yeah.
inform.
Let
It
me know
informs
when I
that
can
it's
start. Hmm.
yeah. So here's a warm welcome to everyone who has taken the time to join this interaction. And I'm really happy to bring Dr. Yasmin Jayathirtha across teachers, mostly chemistry, I suppose, teachers, and there are some students also who have joined. And looks like more people would join because the number of registrations is very large. So let's see, but that's all right. We will start. Um, Dr. Yasmin has a very long history of very dedicated work in teaching children, in following her heart, which is chemistry. She's a scientist. She's a scientist by training. She did research also. But then she decided, she and people like her, deeply inspired by J. Krishnamurti, they decided to start a very extraordinary school called CFL, Center for Learning, near Bangalore. It still runs, where she taught children for nearly 3 decades herself. And her classes, science classes, were truly extraordinary. At some point in my life, I have also had the benefit to interact with uh, Dr. Yasmin, and you will see, all of you will see, she's not only an extraordinary chemist and educator, she's a very fine human being. It's great to know somebody like her. So, with that introduction, Yasmin ma'am, over to you.
Okay. Thank you. And again, thank you for joining. Mm, okay. I wanted to share with you what we were thinking about and how to go about it. I came into teaching not as a trained teacher, but after having uh, having done a research career, mainly in physical chemistry and spectroscopy, and then decided I would like to uh, teach. And to Dr. Sudesh, I want to say also to get out of the uh, grant chasing difficulties of uh, research. So when I started doing that, I never liked chemistry, managed to pass it, managed to do it, but found and thought it was a rote learning thing. Then I realized that if I have to teach, I have to learn to enjoy it because otherwise my students won't. So then I began to do, and what I thought I will do today, Anshumala and I both talked about it, is to use this as a meta thing to say, teach something and say why I would teach it that way. So, in a way, I'm asking you all to take two roles. One is students, and students, as they are in the classroom, don't ask questions. So, remember, you're also teachers. So, you all should be alert and asking questions and saying, why are you doing that? So, in a way, I'm putting quite a lot of onus on you to keep responding to whatever one is saying. So, uh, I had a I had a PowerPoint presentation, but it's not a very, it's a very sparse kind of one. So I'll share it a little later, but why organic chemistry? And it's very interesting, but as we were talking about that, um, I found a thing in the Hindu. Uh, I think it was the Kerala edition. Let me share that with you because it was a Nobel laureate talking, and sorry, let me find that. So, no, sorry. Can you see this? Yeah. So he got it for click chemistry, which is pushing in things into the Nobel Prize for click chemistry. And he said children should be taught chemistry like reading and writing from grade 1, which I don't agree with. But what he said was chemistry is not all, but it's everything. Because the food that we eat, the chair that we are sitting on, the air that we breathe, when we feel pain, when we are in love, when we are hungry, when we fall asleep, that's all chemistry. And I don't think students are learning chemistry that way. I don't think they think of chemistry that way. Because if you go to your classes and you ask them, what is chemistry? They'll tell you it's all those bottles on the lab, it's acids, it's reactions. And then if you're talking with somebody who comes from what shall I say, from a particular thing, they'll go, chemicals, like this thing. And then I have to tell them, but you're a bag of chemicals. And this bag of chemicals is doing everything. Everything in the universe is a chemical. And so why are we learning it in the subject in the classroom? We are learning because it's a language. And we must remember that. And it's a very alien language for students. It's a language. And once we learn the language, we can describe all what he's talking about. Hmm? So, and then Mendel said, it should be done in a pleasurable way so that it's not difficult to run. Just make a lot of pictures and describe the microscopic world of molecules, kinetics, everything. And he's talking about animations and things like that. I don't know how to share it, but I can share it with you all later on if anybody would like to have this passage, because I found it very interesting.
Yes,
And
Yasmin ma'am, we can share things on the WhatsApp group. We have created a WhatsApp group for this
yeah, I
here
don't
joining
have a
here.
WhatsApp group. I'm not on the WhatsApp group.
It doesn't
So
matter. We'll add you.
I'll send it to you.
Yeah,
And
sure. And
yeah,
we
right
will
now
add
I'll
you there
stop
also.
sharing.
Yeah.
So then I was looking at it and I realized, and I've also been teaching, though I've stopped teaching in a school for quite a while. I have been teaching one of the kids around my house for the SSLC, the Karnataka State SSLC. And the organic chemistry that she has is very descriptive, quite content heavy, and doesn't really explain anything. So, in trying to make it interesting for her, make it accessible for her, I realized I needed to start with bonding and structure. They all the 9th and 10th students do bonding, right? They do covalent bonding. They learn about covalent bonds. They learn about ionic bonds, and they sing. But they don't learn, and what they don't learn, which is important in organic chemistry, is about non-bonded interactions. So we really need to talk about non-bonded interactions. Now, what are non-bonded interactions? And how? So this is where I'm going to teach you all how I would teach non-bonded interactions. I hope you don't get bored, but let's look at it. It is difficult to teach this in the 9th and 10th because the idea that they have of atomic structure, we talked about, I know we had written about misconceptions, but it's not so much misconceptions as the picture that we give them is a wrong one, is not a complete one. So they don't quite understand what's happening. So when they learn about the atomic structure, they're told the electrons are around the nucleus. The textbooks are very careful not to say going around, but I think all of us teachers still say it goes around the nucleus. And it's a particle and so on. So at that point, they are not getting the idea of the cloud of electrons around a molecule. So one has to point out that, look, if you have a magnet, you have a magnetic field around. When you have the magnetic field around, you feel the magnetic field everywhere. So just like the electron has an electric field, which can be felt by other nuclei, by other electrons, and so on. Because they would have learnt about like charges repel, unlike charges attract. All of that has come in already. So those ideas are there. So you have to tell them this. And then you begin to talk about, I'm going to use a model. And we'll have to talk about how we can afterwards with the model, without a model, teach this, or what we can use as models if we can't get the thing. But I'm going to use this now to say, look, the electrons are all around. Here's a molecule. There are electrons all around it. Now, they've also learned states of matter. So you had to draw upon the children's knowledge. They've learned states of matter. They know in gases, the molecules are not held by each other and are free to move. And in liquids, they're held by their neighbors, but still free to move. Now you have to ask them, if it is not the bonding, what are the forces which hold the molecules together? Because if there were nothing, if there were no forces other than the bonding, things would either be solids, which is, things like diamond and sand and all that, extended lattice, salt, giant ionic lattices, or they would be gases. Small molecules would be gases. So then you talk about the fact that, look, the electron cloud, and I begin to use the word cloud at that point, the electrons around feel the thing of other electrons. They're kind of moving around, adjusting themselves. It's rather like a balloon being pushed around. It's not like a hard, because I think the words that we use, and the students make pictures. Now you have to unpack what the pictures are. And among the pictures that they have about an orbital, and we should look to see whether we have those pictures also. I know I had some of these for a very long time, and I still do sometimes. So the idea of an orbit is, because we talk about the distance from the nucleus, the idea of an orbit is like a space into which the electron goes and sits. And so then you have to point out that this is a cloud. They move around, not too far away, not too close, but they can get distorted. So then you bring up the first idea of, look, when it does that, the positive charge gets a little exposed. So you have a dipole. And so then at that point, what I would do is to show them the idea of polar molecules. So again, let me share my screen with a fairly simple. So I would show them the idea of a polar molecule of so I have the water, have a balloon, have them rub the balloon. So now they know that you get static charge there because you play around with their hair, you play with pieces of paper, and they would have done that maybe. And then you show them with the stream of water, the fact that it bends. Now you say, where is that charge in the molecule coming from? Because the water molecule is covalently bonded. Where is that charge coming from? And then you show kerosene and you show that it doesn't seem to have a charge because it doesn't bend. You put it in a burette and you let it run and you repeat the same experiment. And it doesn't charge. So where does it come from? So then, and what makes one molecule stick to another? So then we talk about the idea of this fluctuating electron cloud, which shows you a temporary dipole. You've already talked about a polar molecule here. So it's a temporary dipole. It'll induce a dipole somewhere. They stick together for a millisecond or even less, and they fly apart, and they keep doing that. And then you begin to say that, look, the more electrons there are, the more sticking points they can be. So the fact that they're learning that the boiling point increases as the molecular weight increases in the homologous series, that is a table in their text, begins to make sense. Then you begin to tell them, look, this is it. This is what's happening. And then you say, okay, now what happens? You have this. You have a straight chain molecule. And you can see that it's a very dynamic molecule. One of the reasons why I like to use models is, and we were talking about whether it can be done with styrofoam balls and sticks, or clay and sticks, and we'll have to try it out. One of the reasons why I'd like to use molecules is that it's something tangible for the students to look at. If I draw it on the board, it's a two-dimensional thing. And molecules are three-dimensional. And they move in space and they rotate. And all of which you can show with the thing. Then you say, okay, look, if two butane molecules come together, where would they? How would they interact? Then you can talk about, then you begin to ask, what happens? And this is where I begin to use analogies. And you have to keep telling the students that when I use a comparison, don't push it too far. So one of the comparisons I use is, if I have two hydrogens bonding together, they're like twins. If I have a tug of war rope with a knot in the middle, they'll pull equally on, both of them will pull equally on the rope, and the knot will stay in the middle. Now, if one is stronger than the other, where does the knot go? At this point, the students will go towards the one who's pulling harder. And at that point, when you begin to talk about that, then you say not all atoms pull on electrons the same way. Some pull stronger than the others. Don't bring in terms like electronegativity. I don't bring in terms like electronegativity and all that. It's too soon for them to remember. And the other thing is, how shall I put this? We should teach them a lot more than we examine them on. If you know what I mean? That we should teach them a lot more, tell them a lot more. But what we are expecting them to recall should not be everything. And what I have found is, when students get a picture, they recall a great deal. But if there is a stress that, oh, I have to remember it exactly, then it is really a stress. So tell them it's okay, just have you understood. Because none of this is really there in the textbook. So we don't, we say, I'm trying to tell you why this happens. And I'm not going to ask you why it happens. You have to reassure them on that, because that's a thing. Then you begin to say, if one of them pulls a little more, what's going to happen? So I have models, ready to make up. So I put in an oxygen. The oxygen pulls on the electrons more than the carbon does, or the hydrogen does. So you're going to get a slight negative charge here and a slight positive charge here. And the moment you do that, you ask what will happen when the other molecule comes. Then you begin to see that the molecule gets attracted, positive to negative and negative to positive. I'm sorry, I have it. So you get an attraction like this. So you're now bringing in a dipole-dipole interaction. You're not telling them all that, but you're bringing in a dipole-dipole interaction. So what does that mean? It's hard to pull the molecules apart. It needs more energy. So what does that mean? Boiling point is higher. Melting point is higher. And so you use it as a rule of thumb that if the boiling point increases when molecular mass increases, there are more longer chains. The boiling point will increase if there is a dipole. If you have something which boils, water has a dipole, kerosene does not, which is higher boiling. Now, those are data I hope they know, because everybody knows that water boils at 100. Everybody knows that kerosene and all evaporates, or if they don't, I mean, they know it, but they haven't thought about it. So one brings it to their thing and allows them to make those connections. That everybody, so you're looking at that. Then you pull it and say, finally, you look at it. Something which is the same molecular mass as water, 18. So you look at methane, which is 16, is a gas and with the boiling point in negative quantities. So then you look and say, is it just the thing? And then you bring in the idea of a hydrogen bond. And so there you're talking about the fact that because they know atomic structure, you say, well, what happens if the electron cloud is pulled away from the hydrogen atom? What is exposed? What is exposed in the carbon is the next shell. What is exposed in the hydrogen is the nucleus. So which means that it can attract the electron cloud very, very strongly. So you will get a very strong thing, and you say you call it a hydrogen bond because it's directed, it's pulling in that direction. These interactions can happen everywhere. This is directed, and it is much stronger than the interactions. If it is much stronger than the other interactions, then you have to give them some things. So you would tell them that the bond between the hydrogen and oxygen in the water molecule is roughly about 200 to 400 kilojoules. The hydrogen bond is roughly about 20 kilojoules. The non-bonded interactions are of the order of 2 to 3 kilojoules. So you're kind of giving them the hierarchy to which work. And then you say, which are the elements which can pull the electrons away from the hydrogen? So we give them the thing that it's only oxygen, nitrogen, and fluorine. And far as we are concerned, fluorine we don't care about much because we don't see it in the labs. So we're looking at nitrogen and oxygen, and then you can tell them. Because I think we can tell them that we will see afterwards how important it is for life that these bonds are there. these weak bonds, but still strong enough. One of the other analogies I use is like, but that is when you're looking at biomolecules, is that a Velcro, that it sticks enough that you really need some energy to pull it apart. But it's not like you've stitched it up, so it's not permanent. So one has to relate it to something that they can make sense out of, because they can't see molecules. None of us can see molecules, and we made sense of it in some way or the other. And how do you help the students to make sense out of it? So we're looking at a lot in non-bonded interactions. We are looking at polar and non-polar molecules. And then one of the things that one has to do really is to ask about which which will have the higher boiling point, do you think? Because from the time we write tests and exams, we are used to giving one reason for something, for a phenomenon. One of the difficulties of chemistry is that it's a balance between two or three things occurring at the same time. So I'm going to look at here the balance between molecular mass and non-bonded interactions. Then if there is a point where there is a dipole, then what will add to it? So I'll have to look at two or three things and come up with what is the boiling point. And the best example I have found, and again, I'll share it with you. I'll share it with Anshumala, who'll share it with the WhatsApp group, is I believe ants communicate. And I tell this as a story to the students. When ants when ants want to call other ants, or they're agitated, they release 4 chemicals. The first one is a hydrocarbon, and it diffuses rapidly. And any ant around in the surroundings gets that and realizes they have to move that way. By which time they meet the second one and they know something is happening. Then they meet the third one and they know they need to be geared up for a fight and things like that. These, I think, are not pheromones. It's more like, well, let me share it with you. They might be pheromones, but he calls them the language of the communication by chemicals. Actually, it's so pheromones are mainly for mating and things like that. These are alarm signals, or to tell you that come to me, there's something here. So not so much for mating. Pheromones, I think, are only for the mating signals, but I'm not very clear, so I should think about that. So then when you tell them, how do you know which one diffuses first? This is, of course, for the senior students, not quite 9th and 10th. But even with them, you can say, what do you think would be the boiling point? Which do you think will diffuse faster? Why do you think it will diffuse faster? So that, again, you're rooting it into these properties have uses. These properties are being used by organisms to communicate, to be able to do things, and so on. Cooking is another one where we can look at properties. If I have a non-polar thing, will it come out in the water? No. Why do we fry spices in oil? Everybody, whether they've cooked or not, have been in the kitchen. Why do we fry spices in oil? Some of those non-polar compounds are going in. There's a rather nice book called Masala Lab, where he talks about all this and so on. So when I make tea, would I make tea in oil? Will anything come out? If I put, so we can look at that. We can talk about what kind of flavor compounds will come out. What kind of, and later on, as we begin to go, how shall I say, functional group by functional group, we can draw upon all this and so on. So a good part, after they've got a feel for the non-bonded interactions, one begins to talk about structures, which is there because the books, again, I'm trying to remember that without a background, they talk about isomers and so on. Or they'll tell you very quickly that there are these isomers and all that. And this is one misconception, not so much again, because we draw those structures on the board. And I notice that when I draw, it's like you draw a triangle and you write ABC, and A is always on the top. So students who haven't quite got it think that all triangles are ABC and A should always be on the top. Because we are misleading. We are not showing them the fact that triangles can be anything with any names. It can be anywhere. Triangles can be rotated. We really don't do that. And children who are trying to make sense of what they're learning new. One thing that differs, that as a teacher I find, is that because we've taught it so often, we think we know it. And we get used to it and we say, this is easy. And we have forgotten what it's like to have heard it for the first time and trying to make sense out of it. And there, I think somewhere, both models will help, and we should learn that when I draw a molecule, when I draw butane, do I draw it as a straight line? So that then the student, and this is a mistake, you all should tell me if you all have been teaching, this is a mistake that they all make. They bend it and then they say this is an isomer. Because the core of the thing that it should be a chain bonded together isn't there when I draw it as a chain like this. They think the bent one has a different structure. So maybe one should learn to keep changing it around even if one doesn't use models. I'm wondering about that. Suddenly it came to me now. I must tell you that. So you look at a butane and then you ask them, okay, what is the bonding in this? And you can draw it on the board and ask them, what is the bonding in this? And they'll tell you. 4 carbons bonded to each other, each carbon, 2 and 1's bonded to 3, the others bonded to 2. Then and what is the formula? They've learned that. So they'll tell you, they'll count and they'll tell you it's C4H10. Then you show them this. So what is the formula? So C4H10. Is it the same molecule as the other one? You can draw this on the board and ask them, is it the same molecule though it's the same formula? Then you begin to realize that they begin to realize that no, here there are 3 bonded together. Anywhere you look, there are 3 bonded together, but not 4. And the 4th one is off on a side. So it is, and the middle carbon atom has is attached to 3 carbons and 1 hydrogen, while here the middle carbon atoms are attached to 2 carbons and 2 hydrogens. So then you can bring in the idea of isomers. That look, that is the thing of organic chemistry. That you can have structures which are different from each other. So either at this point or earlier, assuming that one has started with what is organic chemistry with the carbon cycle and things like that. We need to talk about the fact that why carbon? And if you have students, or to tell the students, or if you have students who've been listening, you say when you look for life, when you know that people are looking for life on other planets, or if they say molecules of life found, and these are all headlines on the science pages, and one should be clipping it out and putting it on the notice board, then you can say all through the universe, scientists believe that life is made up of carbon. And you can ask why. And you can explain why. The fact that carbon can form long chains. The longest chain that nitrogen can form is about 5. The longest chain oxygen forms is 3 in ozone, and it's very reactive. But carbon can form long, long chains. And you can talk about plastics. And you can talk about hair. You can talk about how long does your hair grow? And it's all one chain. I mean, twisted, but the length is one chain. And things like that. That is where I think one brings in wonder and awe into the children. I came to it, as I told you, I didn't really like organic chemistry, but I came to it partly from doing biochemistry and partly from trying to say, okay, this is fascinating. I never thought about it this way. And looking at it. So one needs to be learning. One needs to be looking at what you read and say, how do I use this in the classroom? How will I work with this? How will it interest the students? And as I said, never test on it, because then you don't want to stress them out with too much detail. But detail given as a story, detail given as, look, I find this fascinating, will make it fascinating for them. So come to the structure. And this is structural isomerism. And again, I think among the questions which were asked was something like, how do you make them learn it? And frankly, to make them learn it is to make them do it. So which means that in the classroom, you have to make them draw the structures, draw the isomers, give them as homework, keep repeating it over and over again. Don't expect that having told them this, they remember. They will make mistakes, as I said. They will consider this an isomer of this because it's bent, and so on. So to point out why it's not, do it as homework, do it as a 5-minute revision before starting the new topic, which is what I used to do. My classes were small. So as a teacher, one has to make sure that you call upon everybody and remember who you called upon, and remember not put up hands, because then only the ones who know will put up hands. And not not put people, I was told you shouldn't be calling on people because you put stress on them. So I said, okay, then how does one do it? I'll start from one end and keep going, and your turn comes, your turn comes. I'm calling on you particularly. It's your turn, or something like that. So whatever it is, to do a 5-minute revision, even if students don't answer, I think to keep listening to it over and over again, or to keep revisiting it in small doses is helpful. Because as I said, we forget the fact that in teaching, the huge amount of practice that we have. Because with every class I teach, I have practiced the structure. My students are not going to get the same kind of practice, obviously, but they should get some, right? And so we have to make space in our class for that. And maybe we have to, because the syllabus is vast, the time is short and all that, maybe we have to learn what we can give as homework. And how do we correct it? Maybe we don't correct everything, but we put it up on the board and say, correct it for yourself. So, which is not a penalization, but it's more like, were you right? If you were not right, why were you wrong? To give them the answer key, maybe. That will take off some of the stress, both of the teachers and of the student, who's not being marked wrong, but still knows, is given the responsibility of learning. But I think we shouldn't underestimate the power of repeating, the power of drill, but with variations. Obviously, not the same thing over and over again, but slightly different ones. Leave it for some time, come back to it and say, I want to know what you remember about this, and ask questions and so on, which is the way one keeps going. So before one starts again on the reactions and so on, so we looked at structural isomerism, which is position isomerism like this. We can look at, well, I had this just to show. So we can look at the fact that if we replace a hydrogen, we get a different molecule. Now this can be here, or it can be here. Then we can point out that if I put it here, if I flip the molecule, it will be the same. So one is looking at that position isomerism. Then one can look at the isomerism of a different compound, making an ether instead of an alcohol. So different kinds of alcohols, different kinds of ether. Now one is doing this, eventually you can tell them that when we come to study this, you will see that some of these make a huge amount of difference to the properties. And tell them that it'll come. It'll come when I go to it and so on. So we are looking at those. Then I think we should come to this as a simple thing. So what we are talking about, stereoisomerism. So those are all isomerism where the molecular formula is the same, the bonds are different. Stereoisomerism where the molecular formula is the same, the bonds are the same, just the position is different. So here are geometric isomers. And again, when we look at that, we can say the properties become different. And Why do the properties become different? Because the interactions are different. The interactions are different because this can bend, this can stack together well, this can't stack together as well. So we draw on the board, or we make models, we make it with styrofoam balls, we make it with this thing, try to pack it together, and so on. Then we can talk about stereoisomerism, which is biologically very important. And you can tell them that and say what happens when you have a carbon atom which has four different substituents, which are mirror images of each other. So I'm showing it to you like a mirror image. Can you see the mirror in the middle? Does it make sense to see it as a mirror image? And then you can explain about optical isomerism, and you can point out that these two molecules are different because when they tumble in space, when they move around, they're not capable of being superimposed on each other. They don't become the same molecule. We can get two together, we can get three together, but the fourth one will be sticking in a different way. So if I put the purple and the green together, the orange and the white won't do it. If I do it the other way, it won't. Replace it with the hydrogen and you can do that. So you can say that brings in different properties. And one of the things that I found is that for showing polarization, because it's not easy to do show polarization in a school lab. I collect things and I keep them, and I found myself with two Polaroid films, and you can show that it doesn't allow the light to pass through and all that. But there are nice videos which show what it does that, and if you can show a video in class, it would be good. If the students can watch it, it would be good. Otherwise, you can explain. So one of the things is you can say that though they're so alike, their properties are different. They interact with us differently. And in life, there's a handedness, including your hands, which are not superimposable on each other. And when you show that, you can, one of the things I found is that the easiest thing to do is spearmint, which is there in chewing gum, and shahjira. So I believe caraway seeds in English, but I found that it's shahjira. So shahjira and spearmint are the same molecule, optical isomers of each other. And you can bring that and have them smell it. And they smell very different. Can you identify it? You can have a little test tube with either shahjira or this thing in it. Have them smell it and ask them, can you identify? And how are you identifying? Your nose is doing that. It's differentiating between the two. It's binding differently to that. So then you're bringing chemistry into their bodies. And then you're talking about why you're learning chemistry. You're learning chemistry because uh, because you want to know how and why you're uh, how and why you're growing, how and why you digest. What is food? And what happens when you learn about digestion? Now the molecules have to be something that you can use. So what is food for you? Molecules that you can digest and you can use. So So you can see that we are looking at all this. We've looked at structures and we've looked at isomers. Tell me, what else would you like to do? Can we open it? It's about an hour now into the thing. So I really want to know, what are the questions that you have? And what can we discuss together? Coming back as, and why would one spend so much time over it? So that then you can draw upon it to say, look, these are the principles that we will use. This is what makes sense about why reactions occur, how they occur, and so on. You should.
So, friends, any question? I mean, not necessarily that what Yasmin ma'am has said, but any question? I mean, related to organic chemistry. Today we are limiting to that.
I think there is a question.
Yeah. So Anil
You
Kumar
wanted
Chari is
name
saying,
reactions.
yeah.
See, name reactions come later on, no? Really. I mean, name reactions you just mug up, which I remember I did. But if one looks at reactions and says, what are name reactions? After all, they're a part of, if I look at, oh my God, I'm trying to remember some of the name reactions that I'd mugged up. Sanmaya's reaction, then this thing, and so on. How to teach nomenclature. Yeah, actually, it's only drill. If I'm going to teach nomenclature, I give the rules. And if we are looking at, what class are we looking at? We're looking at 9th, 10th, 11th, 12th. We'll stretch it to 11th and 12th, not more than that. Structure of quinoline and others, I don't know. Do we need it in schools? I mean, like, why are you asking this question? I'm trying to understand what the question is. I'll come to how to teach nomenclature.
Friends, you
But
can actually
I'm trying
speak.
to understand this
You can
structure of
speak and ask,
quinoline.
friends. I mean, you don't need to necessarily write.
Children find how to by heart. Uh, you know, what I told my students who were writing the exams was, uh, please write up what you want to by heart. One thing is, Vinita, I'll come to you. May I finish this and come? You raised your hand. Vanita, yeah, I'll just come. That write it 3 or 4 times. Because when you write it, and then when you go to write it again, there's a memory which is beyond that of your mind. Your muscles also remember. There is a muscle memory. I'll tell you that. So if you've written a structure 4 times, the fifth time of writing, your hand follows that route. So tell them to write it. If they have to learn something by heart, tell them to paste it where their eyes keep falling on it. I used to say, when you're sitting on the toilet, put it on the toilet door. But that was just to make them laugh and do that. But really, at some point, paste it somewhere where your eyes can fall on it. And not mutter it to yourself, but keep revisiting it. Ask someone to quiz you on it every so often. Not in one rush, but get quiz today, get quiz tomorrow, get quiz day after. So these are all ways of learning. And if you realize, these are ways that we learn also. I think we never realize how much practice we get when as we teach. that is there. Vanita, you had put up your hand.
Yes, ma'am. Good evening, ma'am.
May I see you? If you can turn your camera on.
Ma'am, there's some problem with the net. I'm so sorry. Just give me 5 minutes. I'll get back.
Sorry?
My question is, ma'am, when we do the mechanisms, children really find it difficult. Mugging up of organic reaction is okay, but if they know the mechanism using the electronegativity of two different elements, I think they can do it. I still remember the day when I was being called on the board.
Writing mechanisms difficult. Yeah, that was your question.
Yeah.
Yeah. Again, if one has done the structures, so when we look at mechanisms, we shouldn't be looking at mechanisms just as writing out there. We need to be able to imagine what's happening with the molecule. So can I sorry, my butane has become an ether. Sorry. Hey.
You were showing the isomerism of functional isomerism of, I think, alcohol and ether at that time when your butane
Sorry?
turned.
Which
When your
mechanism
butane
of what?
of alcohol, you showed butanol and then you changed it to diethyl ether
Alcohols?
to ether with your when you changed your butane to ether, ma'am. You were showing butanol functional isomerism. No?
Could you type it in? I don't think I got the question. I'm sorry. I'm not hearing too well.
Sure, ma'am. Sure. I'll just write it. I'll just write.
Yeah,
Thank you.
please. Then I won't mistake it. Something about alcohols. I wanted to how to teach nomenclature. Can I go to how to teach nomenclature? And Asya, I'm not sure about the structure of quinine and others, but really to by heart, as I said, to keep writing it and so on. So while Vanita is typing it in, I look at, okay, so you have. I'm saying you were showing alcohol and ether isomers, yes. And what about that? Oh, yeah. So when we are looking at nomenclature, so one gives them the rules. What is what are the rules? What is the longest chain of carbon atoms that you have? And this doesn't really need a model. You can even write it on the thing. So you can say, take the chalk and follow it through. Can your chalk go through without taking a bypass? So whether your molecule is bent or otherwise, one carbon to another, to another, to the other, what is the longest chain? Then they have to remember the first four: methane, ethane, butane, propane, butane. And again, you keep quizzing them on it so that they remember it. Then you go on to, after that, it gets by the names, pentane, hexane. So you're counting the number. And then you say, after that, you look to see how many carbon atoms there are. So which would be the longest chain in this? Whether I draw it on the board or on the thing, I'd say, look, I can follow 3 carbon atoms. Whichever way I follow 3 carbon atoms. Whichever way I go, whether it's this thing. So which is the longest chain I have? It's a propane. Now, is it a propane, just a propane? No, because there's something there. So then it's a methyl propane. Now, as far as propane goes, methyl propane is enough because there's only one way you can do that. If I have a longer molecule, will I put it on the second carbon atom or the third carbon atom? Does it matter? If I change the molecule around and I turn it the other way, what does it go? So you keep setting them nomenclature to right. Keep pointing out that one will make mistakes because you aren't looking at something. But it's only by making mistakes that you learn. And what I have found again is that if you give slightly challenging questions, not so challenging that they can't do it at all, but not so simple that they've already learned it in their books and so on. Or we can pick up structures from somewhere and say, how would you name this? Things like that. One has to keep drilling. And one has to help them to drill. And if you can't, one can't do it in class, one has to give it as homework. And as I said somewhere, allow them to make mistakes and correct to see how it would be there. So it's something out there. So nomenclature, again, nomenclature for the 9 to 12 is reasonably simple. And Ayurvedic nomenclature is meant to be by strictly following the rules. So when you go to more complicated molecules, we all end up with things. And point out that and one keeps repeating nomenclature, right? Because when you begin to do the functional groups bit by bit by bit, you're going to point out that this is the nomenclature for this class of molecules. This is the homologous series. This is where you put the number and things like that. So nomenclature keeps getting revised. I think the mistake that we all make, both as teachers and as students, is to think that once I've learned it, it's forever. Or if I haven't learned it at one point, I can never learn it. I think one keeps repeating, keeps making mistakes, keeps correcting it, and then you get it. This is particularly true of things like nomenclature and all that, which seems so simple when you're given the rules. But when you actually sit down to do it, you find yourself saying, do I put this there or do I put it somewhere else? I mean, is this to something or is it for something or is it 3 something? So it's becomes confusing. So you learn that by drill, you kind of work with it. I think yeah, I'm continuing to point out that I think we should give students lots of drill, lots of time to make mistakes, lots of help, not assume that, it's very clear. Because as I said, we keep forgetting how much practice we've got. Yes, Shisha, you put up your hand? Yeah.
Yeah. Hello. Hi. I am Shrisha Bhatt, and currently I work at Center for Creative Learning, IIT Gandhinagar. So we usually have teacher training teachers who come for training at IIT Gandhinagar. So I've been working there since a year in developing chemistry, content, so that And we usually try to do hands-on experiments with the teachers. And so the thing is, I was reading about Johnstone's triangle. So I'm not sure. So I wanted to know if you have utilized any of Alex Johnstone's work, or the Johnstone's triangle, where he talks about basically three aspects of any chemical reactions which are happening. One is macroscopic, what we are seeing, like the color change or precipitation, and another is submicroscopic level, where you try to then explore what is happening at the atomic or molecular level, and third is the symbolic part. So what he says is that for a student, it's very it gives a lot of cognitive challenge in order to understand all aspects of any chemical reactions which are happening. So he says that you need to cover all three aspects of these in order for for a student to grab hold of the concept. So I was wondering if you have come across this, and has because I've not seen many practical examples of this, maybe a few papers here and there, but I was just wondering if you have come across this concept and used it anywhere.
You mean, okay, let me try and see if I've got your question correctly. That you're talking about what is the lab-based work we can do?
No, actually, ma'am, Yasmin, ma'am, your speaker, mic is giving you a problem. Speaker is giving you a problem. So
Sorry?
actually, ma'am, Yasmin, ma'am had herself suggested us to look at Johnstone some days back. So I mean, she's
Okay.
gone very much through it, but currently she's unable to hear us.
Okay. Right.
Let me type that to her.
Okay.
Or you type your question, but I'll tell her
Oh,
that she must do something
yeah.
about her speakers.
Sorry, wait, I'm not hearing it correct. I'm not hearing. Yeah. Oh, you're typing it. Thank you. I'm not hearing you very clearly.
Okay. Okay. No problem.
Would it be possible to type?
Yes.
I mean, I can hear you, but not
Sure.
exactly get the.
Yeah, I'm typing it. I'm typing it.
Yeah, please. Now, I must tell you that I'm on the headphones because there's something going on outside. And so you will hear it very
Yep.
noisily. Yeah.
Yep.
Yes. Yes, I have. I have used Johnson's angle before knowing that it existed, because for me, that's the only way I can do it. So I would show things in the lab and then explain it as what's happening in the macroscopic thing, and then talk about what's happening at the particular level, because that is where it really is, whether using models or using little diagrams or whatever. And then bring it down to a formula or an equation or something like that, which is the third one. Yes. The Johnston's thing, I found out about the Johnston thing when I think I had to edit an article. And I said, okay, let me look at what it is. And I realized that, yeah, I've been doing that all my life. Yes.
Right.
I've been trying, but why in the very, see, for me, it is like Johnston's triangle. Actually, I think he gives it for the gas laws, but you use the to think. I was organic. I had the luxury of teaching it the way I want. I know that not everybody has. I'm going to make that. What we would do when we look at functional groups, that do the things, then try and explain the reaction and the properties of, so that you're looking, then you're trying to explain it in terms of the property, and then you're going to write it down as what's happening. So that's how you do.
Off, huh?
So
is also off.
I had the, how shall I put it? I had the luxury of using
She's Karuna's
using the lab, and the luxury of time for the thing. But so can one do
Yasmin.
demos? And then once you've
Yasmin
done the
Jayathirtha.
demo, can you say, how do we explain the difference? So we're looking at something, can I take an example?
PhD in
So
chemistry.
we're looking at reactions of alkanes and alkenes. And rather than learn the reactions of alkanes and alkenes separately, it would be nice to compare it. So you put an alkane, you put an alkene, and whether you do it as a demo or you have them do it in the lab. And then say, why are they reacting differently? To come down to, what is the reaction happening here? If you put bromine water in an alkane, and it doesn't decolorize, but if you expose it to sunlight, it does. So this will answer the mechanism question also, actually, at some point. So whoever asked that, please listen, that when you're looking at it, you're going to say, what is happening here? What is reacting? How are you going to do it? So what it is working out of what's happening and showing. It's like, taking apart, when physics is or mechanics is easier, because you can take apart something and show how your gears move and all that. And here we are working with things that are happening which we can't see, and we have to figure it out from what we are seeing, which is really the Johnston's thing. No, first you see, then you figure out, then you put it in terms of what the particles are doing, then you make a law out of it. The particles are doing this, and then you get the mathematical or the mechanistic equation or the thing equation out of it. So, so to a large extent, how do you teach the students? And so you have to do it yourself to make the leap from the macroscopic, which we are looking at, to what is happening at the molecular level. And then come to, how do I explain what is happening at the molecular level in terms of the structures of the molecules involved. So one of the things that one would point out is that to say that for a reaction to occur, some bond has to break and other bonds have to form. Now, that is something that it's taken for granted that people know, but I'm not sure whether it's made very explicit. That you write a reaction, you have the reactants and you have the products. Then to say, look, one bond has to break, at least one bond has to break on the reactant side before the reaction can happen. And can we make some of these things explicit to the students? Can we not assume that, yeah, this is common sense, they should know it? Because they're learning a new language, after all. Chemistry is a language. And to learn a new language, it takes a lot of practice. And so when you do that, you can say, if this bond break, if this molecule, the bond has to break, which is the bond which is going to break? Can you think about it? What is the thing? So if I look at an alkane, all the bonds are non-polar, all the bonds are equally strong. Which is likely to be breaking? So does it react? Not very easily. Why? Because bonds don't break very easily. And then when you ask the question, suppose you put it in bromine water and show it to, put it in sunlight, and then you'll see that it decolorizes. Even if you don't get the HCl, even if you don't get the indicator paper turning red, these are all descriptions of experiments which are there. You can show that unless you expose it to sunlight, it won't. Cover it with foil and put it out in the sun and it wouldn't have decolorized. So once you do that, then you can ask, what is the sunlight doing? It's broken your bromine molecule. Then if it's broken your bromine molecule, then you have something which is looking to make a reaction. So it's going to break something apart. It's going to substitute.
Right.
So you're trying, what they have seen, you're trying to make sense in terms of structures. Then you say, why does an alkene react so quickly? And at that point, you can say, look, there is this cloud of electrons which is not held very tightly. So there is a point and there is a wedge. There's a starting point where you can start the reaction. This is like trying to lever up a lid. No? You need one little bit of, I call it the wedge. You need to wedge something and push it up. So reactions are like that. No? What is the wedge? What is the point which can be wedged? I don't know whether I'm making sense. You must say if I'm not.
Yeah.
And things like that. Because not only does this bring the particle thing into play, which the equation really doesn't, no? Because the equation is showing you the overall thing and saying this gives you this. And finally, yes, as a name reaction, you have to just mug it up by heart, including it needs this condition, it needs that, and so on. But to make sense out of it, you need to. So if this electron cloud is negatively charged, when you ask these questions, what should be approaching? Or if the water approaches it, which way will it approach? So you're also asking them to think. Will it approach via the oxygen side or will it approach along the hydrogen side? So we have to learn how to ask questions of students so that it's clicking in their minds.
Yeah.
I mean, simple questions which will make them say, oh, yes, it'll approach from this side because otherwise the negative will, this thing, the negative. My power seems to be fluctuating. Sorry. Yeah. And is it making sense?
Yeah. Definitely.
So even for writing mechanisms, one has to look at it that way. Where does the reaction start? What are the bits that are interacting? Then how do we find this out? So one of the things when you write the overall equation, which is a very standard one, right? And this is really at the 12th level, it doesn't come at the 10th, that an alkane plus bromine or Cl2 will give you halogenoalkane plus halogenohydride. Yeah. And at that point, you say that, look, kinetics, they found out. When you're doing kinetics, you talk about it to say that one molecule of alkane seems to react with half a molecule of the halogen, not one, when you're working with that. So when that's happening, what is there? Then you say, does the halogen break up? So you have chlorine like this. So what does the sunlight do? What does the sunlight do? It breaks up the chlorine, and one atom, which is very reactive now because it isn't bonded, might go back to bond with it, might also interact with this. It can interact here, it can interact here, it can interact here, it can interact here. Yes, homolytic fission. Sorry, yes. I showed the heterolytic because the bond was with one of them, but yes, it is homolytic fission. So the electron is now trying to bond with something. It can bond back with the other chlorine. But if you have a lot of the alkane in that, it will react with the alkane and put out the hydrogen. Now, which edge would it react with? Those are all refinements. But we are talking about how does one bring it. I think mostly the textbooks give you the equation. So now we have to bring into the classroom both the phenomena as a demo. I'm not saying let them all do it. As a demo, maybe explaining and showing what it is there. And we have to take that demonstration, take that phenomena and say, how does it work out at the particle level? And after that, you get the equation overall and balancing. We seem to start the other way. And I think that's why most people don't like because they say, I mean, the number of people who, when I tell them I'm a chemistry teacher, say, I didn't like chemistry in school. I say, okay, you didn't have me teaching, but which is boasting. But what I'm trying to point out is, what can I say? Because I know that they have just learned the equations and nothing else. And I don't blame them that they haven't liked it. Yeah, anything, one more? Yeah. Would you type your thing? For some reason, look, there is a something going on, so I don't want to take off the headphone, but it's not working too well. So I'm hearing things, but I'm getting half the words are going lost. So please do type your questions. And please tell me whether anything of what I said made sense. Well, these examples are the ones which are there in the book, right? They're the ones which start off. And they're the ones that all the kids learn. So the student I'm tutoring knows that I will not just teach her what is in the book. She's resigned a question that isn't in the book to see whether she has understood. What was the chat? How to teach Markovnikov's rule and the easiest. Markovnikov's rule is actually fairly easy because again we need to know. Let me get the molecule. And even if you're doing it on the board, one does it with the structures. So you're looking at it. Which is the point of attack? See, one of the things that is a little difficult for students to understand is the fact that they have learned bonding through the Lewis dot structures. So when you do that, the double bond is 4 electrons shared, and it appears, or you draw 2 lines, and the implication is that both of them are identical. Now, I use this in the 12th to say, what does in the Lewis theory of bonding explain? And then use the fact that it doesn't show that one of the bonds is weaker than the other. So you go to the valence bond approach. Then you go to what does in the valence bond approach explain? And then you go to the molecular orbital approach. But that is at the 12th level. So when you look at it, you, as I said, somewhere you talk about the structures and you say there is this double bond, one of which is weaker than the other. You know that because you see that it's decolorizing. Now, if this electron is loosely held, and I'm showing this out there, and it's coming to the electron thing, because that is the bond that's breaking, one of the bonds is breaking, then which way will it approach? Here I have a hydrogen chloride molecule or a hydrogen bromide molecule, which is where Markovnikov's rule comes in. So which will be the one that is approaching? Then you point out that it is the positively charged one which is approaching. And the positively charged one is approaching, and it will add on there. The chlorine adds on later on. The H plus adds on and the chlorine adds on because it deviates out there. For the Markovnikov's rule, you need what do you need? The hydrogen adds on to the carbon which is less substituted. And without going into what is there, we can talk about it in terms of steric hindrance. Can you hear me? You're left frozen. Okay, you can. Good. So then we are looking at, if the hydrogen has to approach, where will it be easier for it to approach? We won't talk about, we can just talk about steric hindrance. Where is it easiest for it to approach? One where there is less space occupied. So it will go here. And then the other one. The actual explanation is also that this stabilizes the positive charge a lot better because it spreads itself over more carbon atoms and all that. But for the students who don't quite need that kind of thing, you can talk about it in terms of the first approach will go to the easiest point. And the easiest point is the one where there is only hydrogens and not where there are the carbons. So that we are talking about the fact that it's not crowded. And that is an idea that students can get around with. The actual explanation also includes the fact that which transition state is stabilized and things like that, which you will do later on, but not at the 9th, 10th level. Markovnikov's is 10th level? No, it will be 12th, right? So Yeah. You know what? I'll give me half a minute. I think I'll. Let me just connect my laptop. I have a feeling that it's. Let me turn on my laptop.
Meanwhile, friends, while Yasmin is converting her laptop, there are two things we wanted to announce. See, this meeting has been brought to you by Joy of Learning Foundation. So we are a Delhi-based organization. Many of you are new for us, or rather, we are new for you. So, and we work on all the sciences: physics, chemistry, biology, and environmental science. And this is sort of a new experiment we are trying. So we're bringing a senior educator to talk to teachers, and we want to see how successful it is and how many teachers are interested. The other thing I wanted to say was that we have a broadcast group where we announce future events. So I will request my colleague Manisha to post the invitation to the WhatsApp group. Manisha has posted it here. So anyone who's interested in our future programs, they are like time to time they are offered in much more in Hindi than in English, but we are slowly reaching out to the English audience also. If you want to get regular updates, you can join the WhatsApp group. And now back to Yasmin. Even for Yasmin ma'am, if there's sufficient interest, we will keep more of our sessions on other topics in chemistry. And similarly, in physics and biology and environmental science, we'll try to bring some senior people as well. So that's one part of our work. Other part of the work is thoroughly figuring out pedagogy of each and every foundational topic in the sciences. So for that, we work very hard over months together to actually even innovate over pedagogy. And those of you who have attended would see that we have lots of ideas offered in every session, and there are a lot of question answers and discussion. So so you are most welcome to join them. And back to Yasmin now.
Somebody has put up their hand. No. Okay. I think the sulfonation question, I need to look it up. I'm so sorry. I don't remember. It's been a while. But that is one of the points where this is an electrophilic attack. So you'll need a positive charge. And this is one of the things where you have to point out that that's what I said. We look at SO3 minus and we think it is sacrosanct. So this is where I'm saying that properties also depend on the conditions that they're there, and they have to keep telling this to them. So SO3 in presence of, when you're making the sulfonation thing, you're taking concentrated sulfuric acid and you're getting 1 negative and SO3 positive. So when you're looking at that, you have to point out that it depends on what is pulling away electrons. And so something can be positively charged with one thing and negatively charged with something else. So that is we have to point out that conditions matter, and these are where sometimes the language that we use becomes a problem, because when we talk about ionic bonding, we talk about the fact that things like sodium gives up its electrons. Sodium doesn't give up its electrons. In reaction with chlorine, it holds on to its electrons less tightly than chlorine pulls it away. It's still pulling on the electrons. So at this point, that it is a balance of two things is something that we don't teach when we teach chemistry. And we really should keep stressing on reactions also depend on the condition, particularly for organic chemistry, very strongly depend on the conditions. And you change the conditions, the reaction can be different. I don't know whether it made sense, but so one explains it as that. Then under these conditions, you're getting a SO3 positive. And why you're getting an SO3 positive.
So, friends, if we have one round of questions over, uh, and some people are asking me how they can reach us. So maybe, okay, I will personally give my WhatsApp number to anybody who wants. But otherwise, we are also a community, and that's how we are trying to make an education community, a community of teachers. And we will keep more such interactions. And if you can give us feedback on the WhatsApp group that we had created, it will be very nice. So we'll put up a feedback form also. So feedback as well as suggestions for which session next, which topic next, at least in chemistry, you would want from Yasmin ma'am. So that is another thing which we would want to have from you. And we will see what frequency we can keep, which is comfortable for her as well as for everybody. I'm a little disappointed at the attendance because we had 200 registrations, but I don't understand why people register if they don't want to attend, or why, or what happens that they don't actually attend. Uh, okay, so Neera is telling me that in WhatsApp group only admin can message. That's true. So I mean, WhatsApp, the broadcast group is not for general suggestions. So I mean, maybe Manisha, can you give your phone number here? So I mean, we are giving our personal WhatsApp number, so you can send us messages for anything that you need. Manisha has put in her mobile number. This is her WhatsApp number also. So any specific query you can raise to her or to me. So it's very strange that our main speaker is unable to hear us. So she is kind of seems lost every time we are speaking. I'll just tell her.
Somebody's. Yeah. I hear the thing. It's the details that I'm losing, and I'm slowing down actually at the moment.
No, I suppose it's your earphones which are giving so much trouble. But
Yeah, I've given my email. I'm
Yasmin ma'am has given her
so
own
if
email
you want
address also.
anything, we can mail me at this mail ID.
Yeah, she prefers the mail than phone or even WhatsApp. So yeah, people can actually mail her. Yeah, with that, I think I will stop live streaming.
Hmm.
I don't know why I'm unable to do that.